All right, so this screencast is just going to be about a little bit of review about what we've already talked about in terms of one-dimensional kinematics or one-dimensional motion. So we're still going to think about the motion of an object moving along a straight track or back and forth along a straight track. Right, we can describe or relate that motion is to figure out how its position changes over time. We measure position in relation to some reference point we call the origin. It can start at the origin or any point along the number line, move either left or right. Generally, things over to the right are going to be positive, and things to the left are going to be negative. When something moves or changes position, right, they can move at different speeds. They can cover a different amount of distance each second. And when that ratio of distance to the time that it travels is called speed, right? Speed is just going to be a number with units attached to it. So if we cover 3 meters every second, that would be a speed of 3 meters per second. When we're talking about speed of an object, generally direction is not going to be important. But we would usually talk about the object moving to the right or the left, right? Sometimes, however, direction of an object is important. Which way it's moving is important. If you think about it, you're getting in your car, ready to pull out of a parking lot, and if you just are going to start push the gas, doesn't matter which way you go, it does. If there's kids behind you walking in the parking lot, getting to their cars, then you don't want to hit them. If there's a car parked in front of you, you don't want to hit that. So you want to make sure that direction is sometimes important. And when we have direction being important, we get a different quantity that we use, that we express answers in, how fast something's moving, as we call it velocity, because velocity tells us that it's both got an amount, how fast it's going across the ground, but also the direction associated with it. Velocity is a quantity that we call a vector quantity, meaning that it has to have a direction for it to have meaning. So I could be traveling at a speed of 15 meters per second, or 15 meters to the second right, or to the back or front or to the left would be a way to express velocity. Generally, velocities will have a positive sign or a negative sign associated with them, whereas speeds will not. They'll just have the number. And there are no negative speeds. We've already talked about motion graphs. Here we have an object moving 10 meters every second. And then here's the velocity graph. That slope of that is 10, and that velocity graph over here at 10 meters per second. Velocity itself is given the symbol V. It's defined as change in position over time, right? So whereas speed is distance over time, velocity is defined as change in position. Now the change in position we calculate as our final position xf, x final, minus our initial position xi, right? And that quantity delta x is what we call the displacement. How far has it been moved from where it started? A lot of times, speed and velocity will be the same thing, right? Unless an object changes direction, the distance covered and the displacement are going to be the same. So a lot of times speed and displacement are used, or speed and velocity are used interchangeably, but we're going to try and make sure we know the difference, and the difference comes down to displacement as opposed to distance. So when we ever express the direction of velocity, we're going to use a plus sign or a minus sign, where plus would be to the right and minus would be to the left. We've already talked about constant speed and constant velocity motion. There is a little formula that we could use numerically that we'll get back to next week when we start actually talking about some numbers on problems, some actual problems where we have things moving, where the velocity is equal to the displacement, change in position over time, and you could use that equation, or you could know that it's one of those triangle relationships that we could use that we've probably all seen somewhere in math or science, that d over vt, and then we get the different manipulations of that. Distance divided by time gives me velocity. velocity times time gives me distance. Velocity over distance, or distance over velocity equals time. And we should be familiar with that, but we'll get plenty of practice with that as we go through. So that's kind of a review on what we've talked about so far, where we should be. We should understand that the slope of that position time graph gives us that velocity graph. If my slope were this way, then my velocity would be here at -10, because the slope of this is 0 minus 50 over 5, where I finished at 50, or at 0, I'm sorry, where I started at 50, and the time it took 5 seconds. So now we're going to start talking about what happens if we are accelerating. What if we're changing speed, right? First thing, when we change the speed, a change in velocity, right? That's called acceleration. Now back here, when we looked at constant velocity graphs, here we see that my constant velocity, I'm always at 10, 10, 10, 10, 10. My velocity is not changing. My acceleration in that case is always 0. With constant velocity, A is always equal to 0. However, when we talk about constant acceleration, now we are going to be changing speed all the time. For example, when you stop at a stop sign and then you drive ahead, you put your foot on the gas and you start from rest, where your car's sitting still at the stop sign, and then you slowly gain speed as long as you keep your foot on the gas, right? If you're sledding down a hill in the wintertime, if you're rolling down a hill in your car, right? Anytime you're changing speed, you are doing what's called accelerating, okay? And what that means is that velocity will be changing over time. So A equals change in velocity over time. And that change in velocity is my final velocity minus my initial velocity. All that over time equals acceleration. A lot of the times, even though it should be change in time, change in velocity over change in time, that initial time, t0, is usually 0. That's when we start, right? When we put our foot on the gas, when we let the thing go from the top of the ramp, when we push off and decide we're going to start sledding down the hill. That time is where we start timing things, so it's going to be 0. So we just end up with acceleration equals final velocity minus initial velocity over time, right? And then we could do some algebra with that. So we could say that A times T equals V final minus V initial. And then we add V initial to both sides, and it cancels over here, so that we end up with VF, final velocity, equals acceleration times time plus my initial velocity, right? And we'll talk about what that means. That's going to be a linear equation where my final velocity is on the y-axis, my time is on the x-axis, and my initial velocity is my y-intercept. But the big thing here is that the acceleration graph, right, the slope of a velocity versus time graph will give me acceleration. So back up here real quick. The slope of this line, slope equals 10 minus 10 over 5, or 0. That means A equals 0. And we'll come back and talk about that a little bit more as we go through. So what happens when we have a change in position when we are accelerating, right? When an object is accelerating, that means that the distance it travels, if it's only going in one direction, like rolling down a hill, or the same thing as displacement in that case, each second it moves, it's going to move a little bit farther than the previous second. Or if it were, you're driving along and there's a stop sign coming up, so you put on your brakes, and the brakes are squeezing your tires and making your car slow down, each second you travel, you will travel shorter distance each second as you slow down than you did the second before. So it's moving at a different distance each second, then it's going to have a different velocity each second, right? And the graphs of position and time and velocity time are going to look different than the ones we've seen before, right? So if we have constant acceleration, right here, for example, we have a card, something that starts out at 0, and then in the first second it moves like 2 meters. Then in the second second, now it's up at 8 meters. So it moves 2 here and 6 there, and then it goes to 18, it moves 10 there, and then it goes from 18 to 33, which is like 15 meters there. So it's moving a different amount of distance each second, which gives us this curved graph, right? And we might recognize that as a parabola or a parabolic curve. Now, right, so we have that parabolic or curved path. Now, to take the slope of this parabola, right, it's not a linear function. So there's some math involved that you don't need to understand or you don't have to believe. But basically, if we know that the slope of position versus time, change in x over time, that should give us velocity. So if somehow we can take the slope at every little point on this line, we should be able to plot for every little increment of time the velocity of my object. Or if I took the slope of the graph there, and the slope of it there, and the slope of it here, and the slope of it there, I would get like 5 points that I could plot. 1, 2, 3, 4, 5. And then I could draw a line that would make all that. That would be a graph of the velocity versus time for that object, because it's going to constant. There's a mathematical way to do that and make it happen. We're not going to talk about that right now. But it involves the slope of position time, because we know that the slope of a position time graph equals velocity. So this is what a constant acceleration velocity looks like. It starts at 0 and it slowly gets faster and faster and faster and faster, right, until the end of that 5-second period. Right, so the slope of the line, right, on this graph is going to give us the velocity. You don't have to worry about how to take it. Just trust me that we know this is true because we've already talked about it. There's a way to take the slope of the parabola to end up with a linear graph where my velocity is constantly going up. So then we look at graphs, right, of motion. So acceleration is one of the quantities we could have talked about and graphed when we looked at constant velocity, but I didn't want to confuse anybody or throw anybody a curveball. So if we looked at constant velocity motion, the motion we've already talked about, we know that when an object changes the same distance every second or every increment of time, we get this sort of constant velocity graph. The slope of that graph, it's pointing up, so it's positive. It gives it this velocity graph. And then we know that the slope of this flat line is 0. So my acceleration graph, we could have talked about already acceleration. That would be equal to 0 in the graphs we already talked about. But I just omitted this because I didn't want to get anybody confused. But that's really the acceleration graph of a constant velocity situation, constant speed, right? With our accelerated motion, now we get our parabola because it goes a different distance each second. It goes a greater distance, right? That gives us a positive velocity line or a slope, right? In this case, that's positive. This slope is pointing up. So the slope of a velocity versus time is equal to acceleration. Acceleration. So slope here, slope of position time equals velocity. Slope of velocity time equals acceleration. So when we look at the velocity curve here, it's pointing up, so that means my acceleration is positive, so it's above where it's 0, right? This is 0, 0, 0, 0, 1, 2, 0, 1, 2. So as soon as this thing starts moving, it starts accelerating at 2 meters per second squared. This one is going from 0 meters per second up to some speed in meters per second. This one starts at position x equals 0, and then it gets to greater and greater positions each time. So in general, those three graphs are what it's going to look like when we start at the origin and we move or accelerate in the positive direction. So last look at what we're going to talk about right here, and then we'll go to another screencast where we look at predicting some motion. Velocity graphs, what do they mean? The velocity graph doesn't really tell us anything about where the object is when it starts its motion, right? We'd have to have it placed on some number line or be told where it is so it's located. But if we look at this graph, graph A, this object is moving to the right because it's going and it's getting faster. Because here's where my zero velocity is. So it's starting positive. So it's in the positive direction. It's getting farther away from the origin. So it's positive, getting faster, 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 going away. Right? Graph B is an object that is going at some speed. It's moving in the right direction, positive direction, but it's slowing down, slowing down, slowing down. Eventually it's going to get to a point where its velocity is 0, which means it's stopping. Graph C, an object is moving to the left, right? Because it's below the origin, moving to the left, but it's slowing down. Where's it going to eventually end up? It's eventually going to be going up. So like it's going backward, but slowing down. Like I'm in reverse in my car, I'm going at some speed, and then I start slowing down. Like driving in reverse, putting on my brakes. Here, I'm going backwards because I'm still on the left side, and now I'm getting faster. I'm going in reverse and putting my foot on the gas and going faster and faster and faster and faster and faster, going backwards or going left. So here's another look at those same graphs and some examples of what it might look like. So graph A, I'm driving forward over here in graph A. My velocity is forward, and I'm getting faster. My acceleration and velocity are going the same way. I'm changing speed, getting faster going to the right. Graph B, I'm driving forward, but slowing down. My acceleration is going against my velocity. They're pointed in opposite directions. My velocity is this way, but my change in velocity is backwards, so I'm slowing down. Graph C, right? I'm going to the left or driving in reverse if you want to flip the car around, but I'm driving to the left but slowing down. And then D, I'm driving to the left and getting faster to the left. So a summary. Whenever an object is moving, there are 6 different things that we can measure to help us describe and study that motion. They are the initial position and final position, where it starts and where it stops, its initial velocity and its final velocity, how fast is it going initially when it starts, and how fast is it going at the end. And then the acceleration, how is that speed, velocity changing, and the time it takes for us to do that, right? We'll come back and talk about some of these formulas in a little next week as we get through those, but right now I just want you to understand the definition of velocity and how velocity is related to acceleration, and how do I move between the graphs. From position to velocity graph, I need the slope of position time, right? From getting to a velocity to acceleration graph, I need the slope of the velocity versus time. So slope of a position versus time, delta x over t, that's velocity. The slope of a velocity time graph, right? Delta v over t, that's acceleration. And initially we'll talk about, is it speeding up? Is it slowing down? So we can get an idea of what the graphs look like. And then we'll put numbers on them like we did before.